Our first topic in Chapter 1 is the scientific method. Now, the key concepts page here has quite a bit of details. This is probably more detailed than many of my key concepts pages. It starts out with a kind of 6-step version of the scientific method, and if you go out there and search for different versions of the scientific method, either online or by looking in different textbooks, I think you'll see sometimes different numbers of steps. I've sometimes seen up to 7 steps, but I think you could actually maybe bring it down to 3 perhaps, and that's kind of what I've put over here on the right in my whiteboard section. In this middle part right here, I've kind of got this circular hypothesis leads to a test, leads to a conclusion, and then I actually kind of circled it around again because oftentimes science, you could argue, maybe goes in cycles in the sense that you don't just do one experiment and that's it forever, or one project or one whatever, but things kind of keep going and get refined as you do that. So this is maybe a slightly better visual view of what this really is about. But in general, the method, you can see it has defined the problem. And again, that, like how you do that, there's probably a lot of different ways. But here's formulate a hypothesis. So that was definitely one of those 3 things I had over there. Research and collect relevant data that already exists. Well, over here, I kind of put in a bubble up at the top that there's literature in science. And that maybe is there as part of a lot of this, but in the steps here, you can definitely see that maybe this is in an appropriate place right there, because usually you don't do a new project or experiment or make a new observation completely in an isolated bubble, but you go and check out what other people have already done, and perhaps what you're going to do is going to be informed by specific data that's out there. So I think like if we had a 7-step method, this could actually be split into 2 steps. One that's maybe more focused on just like background literature, one that's maybe more focused on already existing data that is out there that might influence your experiment. Anyway, then there's make observations or do an experiment and record measured data, and that kind of represents what I call test over here. So the role of making observations or doing an experiment is to test an idea out, and that idea is really represented by a hypothesis. And then we have to draw a conclusion. And in the method over here, it says, well, probably the most important thing to do is conclude if the hypothesis is true or false. But I didn't use the word true here because this is not a philosophy class. This is a science class. We're not really about truth, I like to say. We do use the word once in a while, but I just would rather say that the possibilities are that the hypothesis is supported by the data or it is shown to be clearly false. Then the last step here says to suggest future experiments or how to replicate results more precisely. In real science papers, commonly there is a conclusion or discussion section of the paper, and that roughly represents this. So there's different ways you could describe this, and sometimes a discussion might go beyond even what this says, but generally speaking, it's going to be about this kind of stuff, suggesting like what is the future and what are maybe broader conclusions we can also draw sometimes comes into it. I've put down here though in 2 other bubbles independent verification, because in my key concepts page you can see like, well, there's other aspects of scientific methodology which include, and the first one listed there is that all results should be repeatable and subjected to independent verification. And that is huge. You can't just do something and then say, this is right, nobody question it, nobody test it again. People do that. People will go online especially and put it on a web page or try to sell you something and say, this is the truth, believe me, right? But science doesn't work that way. Everything is independently verified and continually done so. And if there's any problems found, that leads the whole community potentially to go back and revisit that. So we're always kind of checking each other. And that's why this is like super, super important for the way science operates and really distinguishes it, I think, from a lot of other areas. I've also put down here theories and laws, and in particular, I'd say any branch of science, but physics has a lot of well-established theories, and physics is well known for having laws of physics. And this is often our aim, is like we use the scientific method, but part of what it is we want to develop theories. We want to find laws. Theories are kind of these broader sets of ideas, a conceptual framework, it says here, to explain a wide range of existing results. A law, I think we'll get into that a little bit later in an example, but a law is maybe a more specific type of statement. But I put it here because sometimes laws and theories kind of go hand in hand. Laws are also kind of usually treated as something that For something to achieve the status of a law, it's usually a simple statement as opposed to something really broad like a theory. And it's something that we think will probably likely never really be overturned. But there are some laws that have some like limited scope of applicability, so that part can get a little fuzzy with some laws, and we may see examples of that in this class or maybe in another semester perhaps. The other thing I put up here is falsify. I just put that in a circle right there, and that's kind of to emphasize that the role of experimentation and observation, the scientific method, is not to prove that something is true. It's to test it, really. And so it says here, if a prediction made by a theory is contradicted by an experiment, the theory is thrown out or modified. Now, we don't always immediately throw it out, especially if it was just a single experiment, because this is also kind of subjected to the requirement of repeated and independent verification. If one person finds something that does not align with well-established theory that has already been verified in a lot of other experiments, we don't just immediately throw it out. We usually have a little bit of a question about that and request or wait for independent verification. There have been some famous examples of this where later on an error was found and it turned out that what we thought was a contradiction of theory was not actually there, and sometimes those have made the media and been a huge sensation, but then turned out not to be true. But the last statement here, the role of experimentation is to falsify, not to prove truth. So the kind of joke I made earlier, this is not a philosophy class. We're not going to prove what is true. We're not going to find the truth. But what we do engage in science is removing what doesn't work. And as that happens, theories tend to emerge that stand the test of time. Some of those have worked so well that we continue to teach them, even though we understand that some of them are maybe not like 100% true with a capital T. Like the theories we're going to learn in this class, we know are not 100% true, but they work well enough for like 99 whatever percent of the things we might be interested in applying it to, that we continue to look at it, we continue to teach it, we continue to have people learn it.